Good morning. When I left off last time, I was wondering two things. One, whether my matrix multiplication was introducing some ambiguity in tensor representation, or if the ambiguity already existed in the tensor representation. And two, whether the rules and conventions of matrix multiplication could be expanded in order to multiply matrices of greater than rank 2. These two questions seem to diverge to me. Should I abandon matrix multiplication entirely in order to describe tensors? Or should the rules of matrix multiplication be expanded to include at least rank 3 tensors and possibly even rank 4 tensors, or beyond? First, let's discuss the idea of abandoning matrix multiplication altogether. I'm going to give two expressions in Einstein notation. The first, they will look pretty similar. This one's let's do it this way. Del v sub x n, over del x sup m and del v sub x n over del x n. Okay, so if I wanted to write these in pseudo matrix multiplication, this one is going to be del v sub x n with a right arrow? No. Del x sub m with a right arrow, and del vxn with a down arrow. No delta there. So in matrix notation, that would be del x1, del x2 times v sub, I did it wrong. Got to follow those arrows. This one goes to the right. Del x2 times v sub x1, v sub x2. My apologies. That would actually need to be the shape of matrices needed for this form, where this would be n, and that would be n. What we would need for this one is what I was originally saying, del x n going down, and v sub x n, wait, this was m going down, del v sub x n to the right, which would give you del x1, del x2 times v sub x1, v sub x2. And so you see this one, when the n and m don't match, provides a 2 by 2 matrix. When the n and n do match, that's going to provide a scalar. Anyway, this comes out to be del v sub x1, del x1, del v sub x2, del x1, del v sub x1, del x2, and del v sub x2, del x2. While this one is del v sub x1, del x1 plus del v sub x2, del x2. This one's just a single term. This one is 4 terms. So you can see that the matrix representation lost the names of its indices when it gained these arrows. And the use of the arrows required some specialized knowledge of matrix multiplication, knowing, for instance, that a column matrix times a row matrix creates a square matrix, and while a row matrix times a column matrix creates a single quantity. So that was already confusing enough with just 2 dimensions, but now we have seen an even more complex example in Einstein notation. The first derivative of a vector field seems to lead to a third matrix dimension. But here's the thing, we haven't got any long-standing conventions about multiplying matrices of higher than 2 dimensions. But we do have long-standing conventions about multiplying indices associated with dummy variables r, dummy variable m, and dummy variable n. Those conventions include, in no particular order, number 1, if I multiply some factors with the same dummy variable, it should shrink the matrix. Or this one over here, it should shrink the matrix. Second, if I have output dummy variables in our the number of dummy variables in the output tells us how many dimensions our solution matrix should be. Number 3, if I have dummy variables in my factors over here that aren't repeated, the n and the m, they will cause the matrix to get bigger. Each non-repeated dummy variable causes the matrix to grow by a factor of the dimension of the vectors involved. So this n and m would each cause the thing to grow by a factor of 2. This r would cause it to shrink by a factor of 2. And this v sub r tells us our starting place. It starts with a factor of 2. So, okay, that brings us back to the main question I had in the last video, which was how to multiply these 3 matrices. I had realized that without established conventions of matrix multiplication of higher dimension, I couldn't really even be sure that it was legal, let alone specifically what the answer would be. So I am going to suggest that we leave this form for now, but only as an organizational method. And when I say leave, I mean keep. Keep this form for now as an organizational method. But unfortunately, I also need to keep the dummy variables. I think if I put the dummy variables back in, it will become clear which terms will grow the matrix and which will shrink the matrix. One shortcut to this might be simply to circle the repeated variables in different colors. Well, there's only one repeated variable here, so I only have to use one color. But here, the repeated variables are the x's and the v's, and then I can say if the matrix multiplication is not circled, for instance, this del del y times this, is going to have to grow the matrix, and this del del y times this is going to have to grow the matrix. So instead of a 1 by 2 by 1, 1 by 2, 2 by 2 by 1, we will probably have a 2 by 2 by 2 when we get done with that. And then when we have the 2 by 2 by 2 times the 1 by 1 by 2, we will end up having a smaller matrix. Same thing over here. If that is the case, then it means that what I did in my last video was incorrect. So if that should have grown the matrix, then my last video, I multiplied, what I did was incorrect because I multiplied a 1 by 1 by 1 by 1 matrix by a 2 by 2 by 2 by 2 by 1 matrix, and I shrank the matrix when multiplying. It shouldn't have shrunk, it should have grown. It shouldn't have shrunk, it should have grown. Now, I think it is possible to develop a self-consistent methodology for multiplying rank 3 matrices, but it does not seem to be necessary if this rule is kept in mind. Basically, if you are multiplying a rank 1 tensor by a rank 2 tensor, if the index is repeated, like this and this, then it will shrink the tensor. And if the index is not repeated, it will grow the tensor. I think that also holds if you have a rank 3 tensor, maybe. Um, rank 1 tensor by a rank 2, or actually by any tensor. Um, if the index is repeated, it will shrink the tensor, and if the index is not repeated, it will grow the tensor. In the case of a 2 by 2, in the case of multiplying a 2 by 2 by a 2 by 2, if one of the indices is repeated, the result will be the same size you started with. I should say rank 2. Multiplying two rank 2 tensors. If one of the indices is repeated, the result will be the same size you started with. I'm not sure what would happen if you multiplied two rank 2 tensors where neither index was repeated. So, just to give you an idea, what would have given this result if I had done the circling a little bit differently up here? If instead of those two being circled, these two had been circled, if the repeated index had been between this y and this y, if the repeated index had been these, then you would end up with this result down here. Though I don't even think that would be explicit enough. There's two ways to shrink the matrix there. What I did was what I did earlier was take this times this plus this times this, right? Del y2, del x2, del y1 for this top term here. And then to get this second term, I took this times this plus this times this, del y1, del x2, del y2, right there. Del, is that an x1 or an x? No, this one, del x, del squared x. This goes with this term. Del squared x1, del y1, del y2. That's where I put that. And then this times this became del squared x2 over del y2 squared, del y2 squared. So I did it that way, but I think there's another way of doing it and also shrink the matrix. If I took this times this plus this times this, that would lead to del squared x1, let me write it in green, that would lead to del squared x1 over del y1 squared plus del squared x1 del y2 squared. And then for the bottom part, we do the same. Del y times this plus del y2 times this. I'm not going to go through that, but so you can see that this is there's still a little bit of ambiguity even once. There still seems to me to be a bit of an ambiguity even after we say that repeated indices shrink the matrix. But no, Once I write what I'm doing in Einstein notation, it becomes clear that what happened down here is really totally impossible. When I took this times this plus this times this and put it all together, I was taking that del y2 times both a y1 and a y2 term? Really? No, that's a y1, that's a y1 times a y1. That's a y2, that's a y2 times a y2. So I still think this is impossible, but I don't even see how I got it now. Oh yeah, I remember. I took this times this plus this times this to get the top part, and I took this times this plus this times this to get the bottom part. That's what I did. But now I see that is not a possible result. So there were kind of two ways of doing it that both work, which I'm just going to repeat. This times this gives you this, plus this times this gives you this. So that works. And then this times this plus this times this gives you this. And this times this plus this times this gives you this. So either of those ways would be fine. Okay, you're going to think I'm a nutcase, but what I meant was if this was erased and replaced with del y1 squared, and this was replaced with del y2 squared, then all of that stuff that I just said was good would be good. So now I'm beginning to see how matrix multiplication and representation can be used as an aid to doing these problems, but it's incomplete in itself. You also at least need to keep track of which indices are non-repeated dummy variables and which are repeated dummy variables. That could also be important to denote somehow in matrix notation. Now I imagine it would be possible to set up a self-consistent and unambiguous rules for multiplying rank 3 matrices, but I'm not sure whether it would make the process less or more confusing. Even so, since I spent a good deal of my time trying to figure out a reasonable convention yesterday for multiplying rank 3 matrices, I might make it the subject of my next video